So welcome to lecture 43 of MCS 471, numerical analysis. So this is the third review for the final exam. So the purpose of this lecture is to help you prepare for the last questions on the final exam. So it's also the last lecture. So I will, as in the previous two reviews, first spend some time on the way the final exam will run, and then there are 5 representative questions. So the most important issue is to show up or is to do the exam, and for that you have to remember, you have to know that the exam is next Friday, 10 December. The final exam is online, so that's the first thing. So, but this is a hybrid course. So if you have to be on campus that day, then there is the possibility to take the exam in room 306. So even if you are often experiencing an internet at your place that is not always that reliable, and you want to make sure that it will go fine, then doing your final on campus may be beneficial. So at this moment, if you have a scheduling conflict, please let me know. But in any case, if you do the exam, you must send me an email before 5 p.m. on Thursday, 9 December, stating that you will take the final exam. Otherwise, you will not receive the questions. There is the internet, which I alluded to. So the internet has all the online lectures, the Jupyter notebooks, the Julia code. Now, know that on the final exam, you will have the opportunity to consult everything that is relevant. However, if you have to go through the lectures one by one to see where something is, then you will run out of time. That's the last important point, or almost the most important point. You must submit before 12:30. If I will not, if you submit, say, by 5 o'clock, send me an email with your answers, they will not be accepted. So this exam tests your knowledge and your expertise with using the Jupyter notebook and running Julia code. So speaking of which, to get prepared for the exam, if you can spend a couple of hours, then it would be really good to make Jupyter notebooks of the answers that are presented in the lecture slides here. So in this review, it's really on the last lectures. The 3 last lectures, we discussed 3 types of partial differential equations. And already you will receive credit if you can recognize the type of the partial differential equation. So on this review too, we will always say what type of partial differential equation we are considering. On the exam, you will get here, consider this equation and do this or do that. The first important thing that you have to decide is which differential equation are we in. In this lecture, I will try to indicate what to look for. So then the last lecture before the second midterm was on Galerkin method. It's quite possible that because of the fifth project, you are now quite familiar with the Galerkin method. But in case, and the fifth project was a hard project, so in case you not get there, then there are two review questions on finite elements and the Galerkin method. So there is also a last homework that is due to on Friday, 3 December. You may also look into those problems. So those problems are also representative. Okay, then let's look into the questions. So we have five representative questions, starting with finite elements. So finite elements are piecewise linear functions, and they form the basis in which we develop the solution. So the Galerkin method is a collocation method where you presume a certain type of solution. So in this course, we don't go really in depth. We picked one particular very suitable basis, and that is the basis of the piecewise linear splines. So these basis functions, the phi's, the phi i's are basis functions supported on a narrow range. So the purpose of this review question here is that you look back at the definitions of the phi i's. So there is no picture here, but the picture that should come into your mind are the tent-shaped functions. So the phi I is a spike centered at the xi. So the picture that should come into your mind is this tent-shaped function. Why is that so relevant for the two review questions here? The integrals, they are written over the entire domain 0, 1. Be careful on the exam, it could be negative 1, 1, or it could be 1, 2. So the integrals, no matter what the integration interval is, since the basis functions have such limited support, so they only live in a narrow interval. So in general, when the I is somewhere in the middle, so the tent-shaped function lives in the interval of size 2h. So it starts at the point xi minus 1 and goes to the point xi plus 1. The xi, we can replace this with I times h when the interval is 0, 1. So the h is 1 over n, for n is the dimension of our linear system. So the other property of the basis function is that that will then lead to a tridiagonal system. Okay, let us now look to those two review questions. So we have to express those integrals. So we have the integral of x squared. So this is a useful integral later on in the second review question, if you want to ask why we do this. So the purpose of the review question is essentially writing down, showing that you know the properties of the basis function. So here you see that the first thing that happened is that the range, so the bounds of the interval, have been replaced by xi minus 1 and xi plus 1. And then these are piecewise linear functions. We also split. So at the left is the definition where the tent-shaped function increases. At the right here, we have a decrease. We're going to consider the derivative. You can see that the derivative is 1 over h at the left and it's minus 1 over h at the right. So we have a peak at xi at here I times h. That's the reason why we split this integral in two parts. And that's it. So here on the review, this is a question that is on two parts. On the final exam, you would either get this question or you would get the other question. So here is the other question where the derivatives of the basis functions come in. Now, the derivatives are also piecewise, and they're actually simpler. So in a way, it looks like a more complicated question, but the derivatives are piecewise linear as well. So at the point xi, the slope is 1 over h. So here's the 1 over h that you see here. So this is the 1 over h. And then we have the minus 1 over h at that. So this is the other. So you see, I can go a little bit quicker here. It's the same idea. We replace the bounds 0, 1 by the xi minus 1 and the xi plus 1. Okay, so this is then the solution of the exercise. The solution of the exercise is again also here splitting the integral in two parts because there is this special point at the middle. All right, then the third question on the Galerkin method. So there will be 3 versions of the exam. So here is third version. On the Galerkin method, you have given a differential equation. Now, right now, the equations that will need to be solved for this problem. So it's a boundary value problem, and here in this boundary value problem, you recognize, and this is also for the stuff that we did on finite differences and the shooting method, always be aware of the derivatives or the positions. Let's now focus on the equation that we will need to solve. The previous 2 exercises are essentially preparing for this question. So the Galerkin method in its global totality can get very technical. You see the x square at the right coming up. So the x square will also feature here. So what does the Galerkin method do? The Galerkin method imposes a basis function, imposes a particular shape of the solution. So the solution is called S, and the solution is a linear combination of these tent-shaped functions, the phi i's. And what we do is that in the Galerkin method, we impose the condition that the solution solves the problem in the least square sense. So we had this before. In a way, this is kind of a global review. Let me backtrack a little bit into the part on data fitting. When we are fitting over-constrained set, so we have more points than we have variables, then our residual, we cannot make it exactly zero. But the property that we have is that the equation that we are solving, so let me highlight this. So the equation that we are solving is over here. So if you bring the x squared to the left side, then we have again a root finding problem. So whatever we do when we solve an equation, we plug in the answer. So the answer is here that solution s of x, and we make sure that solving in the least square sense means that the solution is perpendicular to the basis. So in short, what we have here, we have our residual, which I will call R, and the residual is perpendicular to the phi i's. So with the inner product notation, we write this like this. So the residual is the equation that we want to make zero. And that's actually the answer to this first part. Now we have the second order derivative sitting in there, and with Galerkin we are going to replace the second derivatives by the first derivatives. And that is done with this integration by parts. Here the solution is immediately given. So we have the product of the second derivative with the basis function. And for that, we apply the integration by parts. Here we have the initial conditions that come in as well. So perhaps I should use a lot of different colors here. So I said pay attention to the side conditions. So the Neumann side conditions with finite differences, they often are more complicated. So also with the finite differences, we have then extra equations that we have to consider. Here, it's actually easier. Here, what we have is that the solution is actually given. So when we do the integration by parts, we have boundary conditions that come in. And the boundary conditions are automatically satisfied. So here you have to indicate in your answer how you will use the boundary conditions. So we have then replaced the second derivative by the first derivative here. So this is where the integration by parts comes. And now I have other colors. So the green color is for the right-hand side. So here you see the right-hand side coming up. So the x squared will be replaced by the IH to the power 2. So this is an example. So would be if there would be a third part of this question. There is no third part, but the third part could start with this question here, with the bottom formulation, and now the question would be set up the linear system that you need to solve. Set up the linear system, which means that you apply the discretization to the right-hand side. Then I have one more term that I need to circle. I'm lucky having so many colors. So here there is the middle term. The middle term you see appears over here. And this is where we compute all these integrals. the question is again the property that you need to use then in the third part is that you have to use the property that the basis functions have a limited support. That leads to a tri-diagonal system. Okay, so this was the review of the Galerkin method. So since the Galerkin is relatively new, I try to indicate all possible variations on problems that may occur. So there are more than 3 different types of questions that I can ask with the Galerkin method. Then we have the last 3. So the first part was parabolic partial differential equations. The parabolic partial differential equation is also, in our case, the heat equation. So this is a type of a question that you may get, except of course with the title. So it will not state that this is the heat equation. What to look for? Well, with the heat equation, we have one differential equation that depends on time. The left is the derivative in time, and at the right we have the diffusion term. So what this models is the diffusion of temperature over an interval in the interval 0, 1. So we have space, but we also have time. It is an initial value problem in time, so the first 2 equations remind us of an initial value problem. So the second equation states the distribution of the temperature here, or in general, more general, the value of the solution at time equals 0. Then the second part shows the boundaries. So for all time, we know, so for all time at the bounds 0 and 1, we know what the function looks like. And here actually we know what the function looks like. So this is a test problem. We know the exact solution looks like this. So there is a decaying term, so there is a periodic function with a decaying amplitude. So the exponential is a function in time and it decays. The 1 over pi is the diffusion constant. So I forgot to point this out. This 1 over pi, so you can see where it comes now from. This problem was formulated backwards. So we do have a function and we set up the differential equation that is satisfied for the function. Okay, what are the most important issues here is that in this time stepping method, we have to choose the step in time. So k is the value in time, h is the value, the time stepping value in space. So this is a 2-dimensional problem. And what is critical is actually the last question. So this will be probably the very, very last question on the final exam. But it's not a labor-intensive question to ask. And this is where you will get credit for recognizing the partial differential equation. Because based on the type of equation, it will tell you quite in a very straightforward manner what kind of criterion you should apply to solve the last question. Okay, so let's do the first question first. So apply the forward difference method. To solve this question, you run the code that is posted. So every algorithm is defined by a Julia function. The difficulty here is that you have to decide on the parameters for this problem. So in every step, there will be the matrix vector multiplication, where in every step, we are considering a vector in space with the approximations, the current approximations, and we will do a number of time steps. So the big M is the dimension in space. So this determines the size of the matrix vector multiplication. The big N determines the step size, the number of steps we do. So, and here the critical relation is, so again with the heat equation, if you do not know that it is the heat equation, you will be applying the methods from the wrong lecture. So as soon as you recognize that it is the heat equation, you know what the relationships are, the very precise relationships between the step sizes and the dimension of the problem. So you will already get credit for recognizing that it is the heat equation. So if this question was on, I will not speculate here, but knowing that it is the heat equation will already give you some. So we can set it up. Then what is the expected error? So in doing the expected error, we can solve this it's just like with the Romberg integration, with the Richardson extrapolation. Here we know what the exact solution is, and we can compute. We just look at the output of the function, and then we compute the difference. So this is the very, very straightforward double loop that you write here to check the accuracy. And what will come out of there is the 2 decimal places accurate. Now, this is the hands-on solution. What is the alternative? If you know the theory, you have to know a little bit more, and this often pays off. So for the time stepping method, so remember the heat equation was the first equation we considered, and that was a very simple equation. A simple method as well. So the drawback is that the error is actually not that good. So you may have wondered already, why do we take the k to be so much smaller, so 1 magnitude smaller, 10 times smaller than h? Well, this is because the expected error is linear in k. So we have an exponent 1 in k. So we can only expect at most 2 because that's the magnitude here. Okay, so solving the problem, the same problem in many ways, is something that we like to do. Now, what is the condition for the method to be stable? So we saw that we got 2 decimal places. Often the computations that we do, that's the difficulty in numerical analysis. We have logically correct programs, but the output is completely wrong if we do not respect the theory. So there is the stability analysis. Again, important here that this is the heat equation. So you see the diffusion constant d the step size in time k, and the step size in space. So this is the stability analysis, and you see this is satisfied for already for the big N to be 65. So the critical threshold is where you set k 1 over 64. In our experiment, the k was 0.01. Okay, first problem solved, the heat equation. Again, when you prepare this, it's very now to have a Jupyter notebook with the heat forward functions in there, a Jupyter notebook where you have of this equation here. Okay, so let's go to the last question. So the second type of partial differential equation we considered were of the hyperbolic type. In this course, we simplified the hyperbolic type to the wave equation. The first important issue, review, we see that the hyperbolic, but on the final exam you will get a problem like this. So you look at the first equation, we see time and space, but we see, and this is perhaps a little bit subtle, but you see that the derivative, the left-hand side, is actually a second derivative with respect to time. What is perhaps more obvious is that your initial value problem is larger. So since this is now a second order equation in time, we need two initial conditions. We need an initial condition on the position and an initial condition on the velocity. Again, this problem was formulated backwards. Here you see the exact solution, and one can verify that take the derivatives with respect to space, and you plug in t equals 0, then you have these two right-hand boundary values. So we follow the same type. So in a way, this is the same question. But it is an entirely different equation. So what you will do here for the critical threshold will be an entirely different condition. So you will do a different type of computation. So again, it's critical here that you recognize the type of equation. So it is dependent on time. As soon as you see the time, you can throw out the last type of equation, the last type of problem that we will see. If it's depending on time, you have the distinction between the heat equation and the wave equation. So you see here with the second order in time, we have the wave equation, which is also a combined initial value problem and a boundary value problem. Okay, so with the wave equation, we also had to be careful to take the step size for time smaller than the step size in space. How does this run? So it is the same type of question. Now notice the different definition of H. So again, we have our critical parameter. This will be again a linear problem. So now actually we solve systems here, but let's not dwell on this. So this, you see again how will get credit already knowing which function that you have to use. The parameters and the boundary functions, and the critical parameters come at the very end. So here there are no default values given because it would be very difficult, because the n actually depends on m, or the h depends on k, as we will see. It also depends on the wave speed. So it's much harder here to correctly provide the numerical parameters m and n. So we run, so the problem is phrased in terms of h and k. What you need to figure out are the m and the n in order to have the particular step sizes. So that is the main point here, how to call these functions. And then again, we can solve the accuracy problem in two ways. So here we do it in two ways because this is the review and we're quite relaxed and we have time. So it's also the hands-on approach. So if we have called the function correctly and everything looked plausible, eventually you can still make a plot, then the continuation for the hands-on solution is to write this double loop. Now, if at this point something went wrong, don't panic. So that is the other way how to solve this question. So what we did here is that we find also the 10 to the power minus 2, but we can also predict the 10 to the power minus 2. So equally good, but more theoretical, are the two last lines. Again, you recognize that this was the wave equation. Now something went wrong with the computations. So you missed somewhere a type error, or the computer was in a bad mood that day, so it didn't work out. Don't panic. You can still think about what is the method that we considered, what was the expected error. And that allows you to answer also here that you will have two decimal places correct. Okay, now the last part is the stability criterion. We picked k equals 1 over 100, but actually was this really necessary? Could we not take k equals 1/10? Well, let's see, can we do that? The answer is no. So here you see that we have also a stability condition. Remember with the wave equation, what is the wave speed? I'm probably rushed too fast over it, and yes, and that's something that I should backtrack now. So the wave speed is formulated c squared. So this is another difficulty when you apply the problem here. You should know, if you apply this function, you should know what is the wave speed. And what is subtle here is that this wave speed appears, and now I should probably still use a different color. So the wave speed here is written as c squared symbolically. So it's is given by its square. And that's convenient for the stability analysis. So knowing how you should pick, and you should know this in advance before you start running. Now here, our computers are very efficient and we work with very simple problems, so it's all over before we know it. But on real problems, this might be taking a while. So knowing these conditions actually pays off. So here is the back of the envelope computation that you can do. Given the wave speed, c equals 2, given the wave speed, you can check the dependencies on the step sizes. So typically we first choose the step size in space, and then we see here that the step size in time needs to be at least 5/100. So the methods that we considered for the wave equation, and remember, how do we get to the k square h square? Should you memorize this? No. When we did the finite differences, we were always using the same difference formulas for the second order derivatives. So for the second order derivatives, we always had the h square as the error. So that's why hyperbolic PDEs are, in some sense, give more accurate results, but they are conditionally stable. So you cannot say, well, I have this h square plus k square, I can take h and k just the same. That is true. And if you doubt this, run this and you will see. We did this, by the way, in the lectures. All right, 10 minutes left for the last question. So the last question is on elliptic partial differential equations. And again, in some sense, it's easier because you will see this delta x, big delta, and well, it's easier than not. So you should then remember that this delta stands for uxx plus yxx. So this is the equation where the two partial derivatives in space come in. So there is no time here. So no time, you are with the third. So no time may mean we also run out of time, but this is not the case here. So the question has exactly the same format. Know what method you should apply, which function you should run, what is the expected error? And we will solve this problem also here in two ways. We will solve this problem in the practical sense, and we will solve it in the theoretical sense. And here now you can see the question. The h and the k, so because this is the review, everything has to work out very neatly. This is also the last problem that gets solved. Here you see that the h and the k, they are of the same value. So the methods that we are considering here do not have that conditional stability. So the methods are unconditionally stable. So we will be applying these formulas for the second order derivatives, finding the h square and the k square. So the third question can be immediately answered. We will have two decimal places. But again, the question could be answered, asked differently. What if we want 8 decimal places? What should then the h and the k be? Justify. So there's a variation on this very same question. Okay, so you will get credit for recognizing the question. So I forgot to mention this, but the elliptic type equations are representative for steady state. So think about the temperature distribution in a room that stays steady as it should be. So with the heat equation, we were having cooling or typically temperature that completely dies out. Here we have the more comfortable situation where we have equilibrium. Again, the same problem. We are in step size. the step sizes are given, they are the input, but what is input to the function are the dimensions of our problem. So here you have to decide to run this problem, what are the relationships between the step sizes and the dimensions of our linear systems. What is the expected error? So the solution to the problem, oops, and the solution has still a type error in there after all this time. So the second variable here should be a y, not a t. So we have the exact solution and we compare. So you can see that the code is correct. So the code has the exact solution with the y sitting in there. So we will see that even for a very large step size, we have 2 decimal places correct. And that was also what was expected. So then suppose we want 4 decimal places. What should then the step size be? So you see, this could be the very, very last question on the final exam. And if you know the type of equation, if you know a little bit about the theory, what the errors were of the discretizations, then answering this question is just one sentence. So many people get panicked and get clogged up or bogged down with one technical question. It may be worthwhile, and especially since since this material is at the very end, might still be fresh, it might not be a bad strategy sometimes to look at the last equation. Just recognizing the type of partial differential equation and recognizes the theory that we have considered may already give you almost half of the answer of the question. All right, so this is the last lecture of this semester. So this was a pleasure doing this. I hope you learned a great deal from this. And I hope that your final exam will run very well. That you will, in the week that still remains, that you will get prepared for this exam. So I wish you luck.